as a cactus, you're as charming as an eel, Mr. Grinch.
Okay, class, let's talk about the mean value theorem today. And I want to talk about the mean value theorem and just put it in a quick nutshell. So this is not a long film. We'll give you an idea about what the mean value theorem is all about, but it isn't too deep here. There's a lot of different types of questions you can be asked about the mean value theorem, and you will be asked. This kind of gives you some semblance about what it's all about. But the first thing I want to talk about is what you already learned, the intermediate value theorem. It's perhaps an easy way to think about the intermediate value theorem because the intermediate value theorem and the mean value theorem are oftentimes confused by calculus students. We don't want that. So the intermediate value theorem is quite intermediate. Think about a 5-minute elevator ride. What? Yeah, get on an elevator. Let's say there's a 40-floor apartment building and you get on the elevator and you hit your stopwatch and you're on this elevator for 5 minutes. You get on the elevator on floor 2. All right? So see how that intermediate value theorem kind of spells the word elevator if you're a creative speller like I am. So anyways, let's suppose you get on the elevator at floor 2 and you stay on this cat for 5 minutes. Now I realize you're going to go up and down, up to floor 14 and down to floor 6 and up to floor 30 and down to floor 12, etc. And you map out your whole trip for 5 minutes. And in the end, at the 5-minute mark, you get off at floor 35. Picture this. This isn't hard to understand. So now my question is it a guarantee that if you got on the elevator at floor 2 and off at floor 35, is it a guarantee that at some point in that 5 minutes you pass floor 10? Is that a guarantee? You ought to be able to answer that question. The answer is yes. It's a guarantee. How about this floor? Is it a guarantee that in that 5 minutes somewhere I pass floor 28? If I got on at floor 2 and off at floor 35, I didn't leapfrog floor 28. It's a guarantee that I passed floor 28 at least once in that 5-minute period of time. The answer is yes. How about this? How about floor 40? Does the intermediate value theorem guarantee that you passed or were on floor 40? Nope. Is it impossible to have visited floor 40 knowing that you got on at floor 2 and 5 minutes later you got off at floor 35? No, it's not impossible. That's entirely possible. That could have happened. But the intermediate value theorem only guarantees values that are between 2 and 35. You visited every single one of those floors between 2 and 35 at least one time in that 5-minute period of time, guaranteed. That's the intermediate value theorem. Easy. And if you graphed your trip, you would have a continuous function. Now it's interesting, you get on floor 2 and you go up to floor 12 and you sit there for 30 seconds. And your graph, if you're plotting that over time, it remains horizontal at floor 12 here for 30 seconds. Then you move up again. And you're going, yeah, that graph has a sharp point. That means I can't use the intermediate value theorem. Yeah, you can still. The intermediate value theorem demands and requires a continuous function on the closed interval between, in this case, 0 and 5 minutes. It doesn't have to be differentiable, is my point of emphasis here. So it can have those sharp points or nubs, no problem. All right? So maybe that gives you a clearer understanding of the intermediate value theorem. It's really quite simple. So now let's talk about the mean value theorem. Here's the mean value theorem in words. And it's a mouthful and a confuser at the beginning. I mean, take a look. Mean value theorem. Let f, little f, be continuous over the closed interval from a to b and differentiable over the open interval between a and b. Then there exists at least one point c, which is an element of the open interval between a and b, such that f prime at c equals f at b minus f at a all over b minus a. What? Lots going on there. First of all, this notation means is an element of. So that little e, you can think of that as the word element starts with e. If you're not used to that notation, that's what that notation means. But you're looking at this, and I'm not surprised if you're a little concerned. Let's take a look at this. They say a picture says 1,000 words, so let's take a look at a graph here. Here's a graph, and on the x-axis I have a location A and a location B. Here comes a continuous curve f of x. Not only is this continuous, but you can see it is continuous throughout the closed interval between A and B, and nice and smooth, so differentiable on the open interval between A and B. Then, if I locate these two terms at the end point of the interval, I find on f of x, the two locations on f of x, which are dictated by the interval. I have 2 points on the curve, and I can find a line segment that attaches those 2 points. Truth be known, I know how to find the slope between those 2 points. Yeah, from my Algebra 1 days. I just subtract, if I know the order pairs, I subtract the y's on top and the x's on the bottom, and I have the slope. Well, in calculus, that's called the average slope. The average slope between those 2 points. And I know from this theorem that there's got to be a location in here somewhere. And I've deemed that location C as between A and B. Right there, you'll see the magic of why I chose that location, such that the slope of the tangent line there at that point C is equal to, or is parallel to, the average slope connecting those 2 points. All right? So what we're suggesting here is that when you take the y's on top and subtract them, and the x's on the bottom and subtract them, you get that red line's slope. That's somewhere in between there, between A and B, there's got to be a location C such that the slope of the tangent line will equal the slope of the secant line, or that average slope. So f prime at C somewhere is going to equal the same numerical value as the slope of the secant line, or the average slope between those points. That's what the mean value theorem is suggesting. All right, let's look at a problem. So f prime of C is talking about the instantaneous slope, where the location where x equals that magic point C. And this, although it looks quite trafficy, is just Algebra 1 stuff, right? Subtracting the y's on top, the x's on bottom. This gives you the average slope from x equals A to x equals B. Moving. So this problem says, let f of x equal x cubed minus 6x plus 9x minus 1. We want to find the number within the interval from 2 to 4, the closed interval from 2 to 4, which satisfies the mean value theorem. So in my mind's eye, I'm thinking, so long as f of x is continuous on the closed interval from 2 to 4, and differentiable on the open interval between 2 and 4, there's got to be a location between 2 and 4 somewhere such that the slope of the tangent line at that location is the exact same slope as the segment connecting the endpoints 2 and 4. Let's look at this more carefully. Here on Desmos is what this function f of x looks like. And you can see I picked these 2 points, 2, 1, and 4, 3 for a reason. Those are the 2 points that correspond to the closed interval 2 and 4. And I talk about the prerequisites for MVT to work. F of x has got to be continuous on the closed interval from 2 to 4 and differentiable on the open interval between 2 and 4. My apologies. It's got to be continuous on the closed interval from 2 to 4 and differentiable on the open interval from 2 to 4. Then the mean value theorem applies. Okay, so we know we've got enough that we can utilize the mean value theorem. First of all, I want to caution you. You have to state this prerequisite. You can't go on using the mean value theorem if the prerequisites for the mean value theorem are not met. So you have to make mention of these and make sure they apply, Otherwise, this thing does not hold water. And that's not, oh, just do it if you want, or, oh, that's just fussy details, don't worry about it. This is required. The function's got to be continuous on the open, continuous on the closed, differentiable on the open. Got to have it. All right. So here is the secant line between those 2 points. And if I find the slope of the secant line between those 2 points by subtracting the y's on top, the x's on the bottom, I get 2 over 2 or 1 for an answer. I'm of the opinion that somewhere between x value 2 and 4, there is a c such that the slope of the tangent line at that location is also 1. In fact, mean value theorem guarantees such a point. Now, there might be more than 1, but there's at least 1. So here's how I'm going to find that. I take the function f of x, and I know that f prime at this magic point c should be equal to 1. So let's find f prime. That should be easy enough to do. If I've got f there and I want f prime of x equals, you tell me first, say it out loud, and then the TV will write it right in like magic. I take the derivative of the first term and get, agreed. The second term and get, agreed. Derivative of the third term and get, indeed. There's f prime of x. How about the fourth? Yeah, I take the derivative of negative 1 and get 0. Now, I know that that derivative should equal 1 at some location. So this isn't anything pretty, you guys. I took this and put in my y equals screen on my calculator 3x squared minus 12x plus 9. And then I went to y2 and I set that equal to 1. And I saw where those two lines intersected one another to figure out the solutions here. And I actually got two solutions. X equals 0.845 and x equals 3.155. Well, remember, the only values I want to count are the values that exist on the open interval between 2 and 4. So I know I got to be within the interval from 2 to 4, and truth be known, it's the open interval from 2 to 4 that will guarantee me a value. So 0.845 is not going to fly, and x equals 3.155 is the one I want to keep. All right. On my graph, if you go to x equals 3.155, you can do this with your mind's eye, and look at the slope of the tangent line at that location. I bet you're satisfied with this. So I think there's 3.155 right there. And truth be known, the derivative at 3.155 will be exactly 1. You see that it's parallel to that red secant line. There's the mean value theorem. Okay? So that's what you need to know to execute the mean value theorem. And like I say, different problems with different wording, but it's the same action. You got to make sure the prerequisites are satisfied. Continuous on the closed interval, differentiable on the open interval. Then you got to know that if you can find the slope of the secant line, there's at least 1 point on that open interval, such that the slope of the tangent line will dead equal the slope of that secant line. Speak. Know it, learn it, love it, live it. Practice up. We'll see you later.